This is lesson 5.3 on systems of nonlinear equations. So in the last couple of sections, we've been looking exclusively at systems of linear equations. Now we discussed two techniques for solving those. We discussed elimination and substitution. Both of those are perfectly fine and valid techniques. I've mentioned before that I have a preference for elimination, but they're both perfectly fine. When we're dealing with nonlinear equations, we've got a couple of differences from linear equations. One of the nice properties of linear equations is that we're guaranteed to have either one solution, infinitely many solutions, or no solutions. Those correspond to independent, dependent, and inconsistent systems, respectively. Now, when we introduce nonlinear equations, that changes. We're no longer in the independent case guaranteed to have exactly one solution. We can have 2, 4, 3, many solutions. So that's one benefit that we lose when switching to nonlinear equations. But one advantage, or just, I don't know, it's just a thing. One thing to keep in mind with this too is whereas before you could really take your pick, use elimination, use substitution to solve these, and either one's going to work out just fine. For some of these problems, there's going to be one technique that works out that's kind of the clear winner. This is going to give you the solution, whereas this second technique isn't necessarily going to work. So for example, we'll see later on an example of a problem where substitution works out, takes a little bit of work, but it gives us a solution, whereas elimination would not really be a viable option. So the rule of thumb here is to look at the equations, basically just do what's easier. If you see that there's an easy way to get elimination to work, then by all means use elimination. But if that's not going to happen, then go ahead and go the substitution route. So sometimes it'll work, sometimes it won't. Keep a sharp eye out for recognizing which technique is going to be the easier way to approach the problem. So let's take a look at this example. So we've got two different equations here. Notice that these are both nonlinear equations. So again, what makes this nonlinear is here we have an x squared term and a y squared term. Just the fact that we have a single term that is not a linear term, so in other words where our variable is just to the first power, that automatically makes the whole equation nonlinear. In this second one, we have a y squared term, so that's nonlinear. All we need is actually one of the two equations to be nonlinear for us to consider this to be a nonlinear system. We just need the one. Okay, so looking at this, I want to look at this and think, okay, what's going to be easier to do here? Is elimination going to be the easier way to go, or is substitution? I look here and see that my y squared terms, notice that I only have y squared terms in both equations, and I have plus 1 y squared on both of them. That tells me it would be pretty easy to eliminate those y squared terms. So we could actually look at this and just think of subtracting this second equation from the first. But particularly when dealing with systems of equations, instead of subtracting, I prefer to think of it as multiplying by 1 and adding. Now, I'm not fooling anyone. It's, of course, the exact same thing. But when I do it that way, just personally, I know that I make fewer mistakes. So rather than thinking about subtraction here, I'm just going to go ahead and go through the process of rewriting the whole second equation where I multiply the whole equation by -1. Okay, so now I'm going to add. X squared plus 2x, I can't simplify that. I've got to leave it as x squared plus 2x. Y squared minus y squared, those cancel. 9 minus 1, that's 8. So notice I'm left with a quadratic equation. Now this is different from the last couple of sections. When we would do elimination before, we would be left with just a linear equation. Here, no big deal. It is a quadratic, it is different, but we're still going to proceed as normal. So how do we solve a quadratic equation? Well, let's try to factor it first. If that doesn't work, then we'll move on to our quadratic formula. But here, let's see, we want two numbers whose product is 8 and difference is 2. I think 4 and 2 are going to do the trick. X plus 4, x minus 2. So let's check it real quick. X squared minus 2x plus 4x, that'll be plus 2, minus 8 looks good. So our two candidates are x equals -4 and x equals 2. Now for each of these, we need to find a corresponding y value. So remember, in order to be a solution to the equation, we need to have values for both variables that satisfy both equations. So let's take each of these x values and plug them into one of the two equations. It doesn't matter which one. Let's take x equals -4 and plug it into the first one. So that's going to be -4 squared plus y squared equals 9. So 16 plus y squared equals 9. Subtract 16 from both sides, I get y squared equals -7, and oh wait, that can't happen. So what that means is x equals -4 is not a solution. There's no way that we can have y squared equals -7. We are not going to worry about imaginary numbers here. So if we allowed that, then yes, we could solve this, but we're not going to deal with those. So x equals -4, we just toss out. Let's focus on x equals 2 now. So let's plug in x equals 2 into that same equation. So 2 squared plus y squared equals 9. 4 plus y squared equals 9. Y squared equals 5. We subtract 4 from both sides. Now here I can take the square root of both sides, but don't forget, when you take the square root of both sides of an equation, don't forget your plus or minus there. So we have y equals plus or minus square root of 5. So you might ask yourself, well, which one's the answer? The answer? They're both the answer. So we have two different solutions here. So our first solution is going to be 2 comma negative square root of 5 and 2 comma positive square root of 5. So there are two answers. Notice that since our other potential candidate for our x value did not give a valid y value back, we just don't have any solutions at all. We can't have half a solution. We can't just say x equals 4 and then shrug for y. So since there's no valid y value here, we just throw the whole thing out. 2, on the other hand, it had 2 perfectly valid y values. So we're going to go ahead and use both of those. So we do have two solutions, but they both come from when our x value was equal to 2. X equals 4 has no solutions. It's only our x equals 2 value, and there are two different ones. Now if you wrote this on the drill quiz as 2 comma plus or minus square root of 5, I would accept that. That's perfectly fine, but I prefer to write it like this just to emphasize that we have two different values here. 2 comma negative square root of 5 is one solution. 2 comma positive square root of 5 is a completely separate solution. So we'll take another look at a nonlinear system next. This next one, we're going to see elimination is not the way to go. We really have to use substitution to get through it. Take a look at this one. 2x plus y equals 3, x squared plus y squared equals 5. Now once again, notice that our first equation is a linear equation. So you might ask, why are we running into this system when we're talking about nonlinear systems of equations? Well, the reason is the second equation is nonlinear. Again, all we need is one of the equations to be nonlinear for us to consider it a system of nonlinear equations. Notice too, there's really not any hope of elimination occurring here. There's no way I can get this y to become a y squared term unless I multiply the whole thing by y, but that's just a big old mess. Don't do that. We're never going to multiply both sides of our equation by one of our variables. So elimination is really a no-go. So what we're going to do instead is substitution. So notice that I can solve for my y pretty easily from equation 1. So let's do that. Let's subtract 2x from both sides. That's going to give us y equals 3 minus 2x. All right, now I'm going to take this and plug it in for my y into my second equation. So I'm going to take x squared plus y squared equals 5, but in place of the y, I'm going to put that 3 minus 2x term. All right, notice this is now a quadratic equation, I know how to solve those. Let's try to factor it. If factoring doesn't work, then we can feed it to the quadratic formula and it'll crunch some answer out for us. So x squared plus 9 minus 6x times 2, that's going to be 12x plus, it's a plus, 4x squared equals 5. So this is a quadratic equation. Let's simplify everything on the left-hand side rather. X squared plus 4x squared, that's going to be 5x squared minus 12x. And my constant term on the left-hand side is 9. Let me subtract 5 from both sides. So that's going to make this plus 4. And I'm left with 0 on the right-hand side. All right. This doesn't look like a terribly pleasant thing to factor. But if we grit our teeth and think about it for just a little bit, it's actually pretty easy to factor. 5x minus 2 times x minus 2 does the job wonderfully. 5x times x will be 5x squared. 5x minus 2, that's minus 10x. Negative 2 times x, that's negative 2x, so minus 12x altogether. Negative 2 times negative 2 is plus 4, so bingo, we got it. So our final answers then are going to be when this is 0 or this is 0. Well, the first term is 0 when x equals 2/5, and our second term is 0 when x equals 2. Okay, now once again, we do not have half answers here. We need to give values for x and for y. So when x equals 2/5, I need to find the corresponding value of y. So x equals 2/5, I'm going to find the corresponding value of y by plugging in right here. The substitution that we used before, we're now going to plug in our value of x. So 3 minus 2 times x, but I know that x is 2/5. So y equals 3 minus 4/5. So that's going to be, let's see here, 3 is 15/5. So y is going to be 11/5. So if x is 2/5, y is 11/5. Remember, we have two solutions though. Let's look at the other one. When x equals 2, once again, we're going to plug it right in here to our substitution. We get y equals 3 minus 2 times x. Once again, our x in this case is 2. So y equals 3 minus 4. That's just negative 1. So our two answers then are going to be 2/5, comma 11/5. So answer number 1. And 2, comma negative 1. Now, if you think about these graphically, the number of solutions should make sense. Before, when we were talking about systems of linear equations, if we think about what does it look like when two lines intersect, that's going to be at a single point. Look at what we have here. 2x plus y equals 3, we noted is a line. X squared plus y squared equals 5. You might not recognize it at first glance, but that's just a circle. So if we have a circle and a line, most likely it's going to intersect twice, not quite at antipodal points, but going to hit the circle as it's entering it and then hit it again as it's exiting it. That won't always be the case. It could be a tangent line, for example, and it would only hit it once, but this should be reasonable. If you could graph each of these, we'd see that the line intersects our circle at these two different points. So when in doubt, if you're not sure if the number of solutions makes sense for the problem that you're working on, see if you can think about what's going on visually, what's going on graphically. Here, is it possible for a line and a circle to intersect in two places? Yeah, that seems perfectly reasonable. It's probably going to look something like that. So sure, this seems just fine. Nothing weird here. But if you got 3 answers back, that's weird. I don't see that happening at all. I don't see a way for a circle and a line to intersect at 3 different points. So if that occurred, you probably made a little error somewhere. No big deal, but go back, double check, see what went wrong.